You're given a system of linear equations and you're asked, does it have a solution? If so, how many? Infinitely many, 0 or 1? Most textbooks give you neat rules to figure out how many solutions there are. There's a unique solution if and only if these two conditions hold, and infinitely many solutions if and only if these two conditions. But the thing is, why? For some reason, I've never seen a proper proof of these in textbooks or other resources. So today we're going to do that. Hopefully after this video you can sleep at night knowing why these are actually true. Okay, that was a bit dramatic. Anyway, firstly I should mention there is another theorem about existence of solutions in the first place, and that's to do with contradictory rows. A contradictory row in the row echelon form is just a row like this, where you have all zeros on the left and a non-zero on the right, because this implies 0 equals b, but b is not 0, so that's a contradiction. As long as you don't have any of these, you have a solution. We're not going to actually prove this today. We're going to take it for granted because this video is going to get too long. We're just going to focus on the unique solutions and infinitely many solutions theorems. We begin with the unique solution theorem. So we want to prove that if you have no contradictory rows and you have all columns leading, at least in the row echelon form, then you have a unique solution. Well, technically, when we want to prove both ways, we'll first just start with this direction. Okay, so let's do this. We'll make our assumptions, so we'll assume that we have A as a matrix and B as a vector, and we suppose that augmented matrix transforms to UY, where U is in row echelon form. Also, we assume that U has all columns leading, and also there's no contradictory rows anywhere. Now we just need to show there's a unique solution. Trust me, it's not too difficult. We can actually draw the matrix in some sort of form. It will look something like this, where all the pivots are the green ones. They don't actually have to be ones, right? They could be any non-zero element, but we're just going to make it ones. You can scale the rows to make them all ones if you really want to. This will just make it easier to think about. Okay, now we just want to show there's a unique solution for each of the variables. We're just going to examine each row, okay? So we start off with the 0 rows. By the way, they're all at the bottom because the matrix is in row echelon form. Check out my video on that, which I just posted recently. And yeah, so these 0 rows are all just going to give us 0 equals 0. That's really not too much of an issue. That's not a contradiction, and also it doesn't really tell us anything though. Let's look at these first few rows. Maybe I'll label the variables as x1, x2, all the way up to xn. So suppose there's n columns. Now this last equation here, think about it, it's just going to be 1 times xn equals, well, question mark. In other words, xn equals question mark. We do have a unique solution for xn then, okay? It's whatever is in that entry. So that's good. We have a unique solution for one of the variables. Now let's move on to the next one. xn minus 1. Now similarly, that column will have a pivot as well because all columns have pivots by our assumption. So we can write xn minus 1 in terms of xn. xn has a unique solution, so xn minus 1 does as well. And obviously you can repeat this for xn minus 2, xn minus 3, all the way up to x3, x2, and then finally x1 will be in terms of all the following variables, x2 up to xn. And all of those have a unique solution at this point, based on this repeated process, and therefore x1 does as well. You could have done this by induction if you wanted to, but the idea is xn has a solution, therefore xn minus 1 does, all the way up to x1. And so yeah, we're done with this direction. We've proven if all columns are leading, then there's a unique solution. Okay, we just need to show the other direction now, and we'll actually use the contrapositive. So you negate each statement and switch the direction. So we want to prove that if you have at least one non-leading column, you actually have a non-unique solution. We'll actually prove there's infinite solutions. Firstly, we're just going to make some assumptions, and yeah, so we're going to assume that U has a non-leading column, or at least one non-leading column. Okay, let's look at an example because that will help us get some intuition. So we have a matrix like this, and just note the non-leading columns are the columns of x3, x4, x6, x7, and x8. So if we look at the rows of the pivot variables, this last pivot row helps us write x5 uniquely in terms of x6, x7, and x8, which are all non-leading. Then the row above helps us write x2 in terms of x3, x4, x5, x6, x7, and x8. But we can simplify that because we know x5 is in terms of 6, 7, and 8. And x1 we can write in terms of all of the following variables. And we can simplify this because we know x2 and x5 are in terms of 3, 4, 6, 7, and 8. So we have unique solutions for x1, x2, and x5 in terms of 3, 4, 6, 7, and 8, which are non-leading. So we can take those non-leading variables to be actually whatever we want, and then the leading ones are determined in terms of it. So this is how we can generate a solution. Actually, infinitely many solutions, because those non-leading variables can be whatever we choose, and the leading ones are already determined in terms of those. Okay, now we'll get to the actual proof. We need to think about the pivot entries, okay? The pivot entries of U. And we're going to say that QK is the kth pivot entry from the right. In other words, Q1 would be the rightmost pivot entry, okay? Notice these are entries, by the way. I'm not talking about columns or variables. QK is the kth pivot from the right. This is just a notation so we can order the pivots in some way. So basically, as you go from right to left, the K is going to increase. Okay, anyway. Now, I need to think about the non-leading variables, okay? Just for labeling purposes, I'm going to label each non-leading variable a lambda, okay? So if the column of x2 is non-leading in U, remember we assume there's at least one non-leading column, then x2, I'll actually let that be lambda 2. Because the idea is we're actually going to form a solution to the system. Remember, a solution is just some values of x's which work. We are going to show something pretty crazy. All the leading variables as well can be written in terms of these lambdas. In other words, we can write the leading variables in terms of the non-leading. You're going to understand what's actually going on if I actually start. So we're going to do some sneaky, strong induction, okay? So we're showing that leading variables have solutions in terms of non-leading variables. That's all we're doing. So for the base case, we have Q1, okay? We need to show the variable of the column of Q1 has a solution in terms of lambdas. Because Q1 is a pivot, everything to the left of it is 0 in that row by definition of a pivot. And I'm just going to call this column C, okay? Column C. So this is XC, the variable of this column. Now all the columns to the right of here are non-leading. Because Q1 is the rightmost pivot, there's no pivots after it. Okay? Now focus on this row, the equation of this row of Q1. It's going to be Q1 times XC plus a bunch of stuff involving non-leading variables equals question mark. Now the non-leading variables are labeled as lambdas, okay? So you're going to get something in terms of lambdas. Now if you rearrange for XC, you can do that because Q1 is not 0. You're going to get XC in terms of lambdas. So we've proven the base case. You can write the variable of the rightmost pivot in terms of those non-leading variables. Okay, now we just need to do the inductive hypothesis, which will be a strong inductive hypothesis. We just need to assume that the variable of the column of Qi has a solution in terms of lambdas. And we're assuming this for all I up to k. So Q1, the variable of that one has a solution. Q2 does as well, all the way up to Qk. Okay, and the solution is in terms of lambdas. Now we need to prove for Qk plus 1. Okay, so we have the matrix looking something like this. Everything to the left of it is 0 in that row at least, because Qk plus 1 is a pivot. Now consider the next pivot to the right, which would be Qk. Now I'm just going to label these columns as C and D. And so these are the variables. Now think about the columns in between these two. There's no pivots in between these two, because Qk is the next pivot. Therefore, these are non-leading columns. And to the right, we actually have non-leading and I guess also some leading columns possibly. Okay, now focus on this row. We're going to get Qk plus 1 times Xc plus, well, what? Well, all of these non-leading variables are in terms of lambdas, so something in terms of lambdas. And now how about for the rest? Well, we could look at the inductive hypothesis. The variable of the column of Qi has a solution in terms of lambdas. And this is for all I up to k. So going back, these non-leading and leading columns to the right of Qk, well, the leading ones will be, well, Qk minus 1, Qk minus 2, all the way up to Q1. And that fits to our inductive hypothesis. So those variables, those leading ones, have a solution in terms of lambdas by our hypothesis. And obviously the non-leading ones, well, they're just going to give stuff in terms of lambdas anyway. So therefore, this is equal to question mark, and we can rearrange for Xc and solve for Xc in terms of lambdas. So we've actually proven it for Qk plus 1 as well. And so by strong induction, all the pivots or the variables corresponding to those columns have a solution in terms of the non-leading variables. Now, to generate a solution to this system, we can take the non-leading variables to be the lambda i's, and then the leading variables are uniquely determined in terms of those lambdas. There's not really any room for those leading variables. But the non-leading ones, we can choose those lambda i's to be really anything we want. Because there's infinitely many possibilities for these non-leading variables, as long as you have at least one, there are actually infinite solutions we can generate. So we've proven that if you have a non-leading column, you have a non-unique solution, provided no contradictory rows. And by contrapositive, we've proven this direction. Now we also proved the other direction before, remember? So we've proven both directions of the unique solution theorem, and so we've proven it. Finally, okay? This is good. And it's actually really good because surprisingly, the infinite solutions theorem is literally much quicker. It actually uses the unique solution theorem. So we need to prove this, right? We need to prove infinite solutions equivalent to non-leading columns and no contradictory row. Firstly, let's look at this direction of the proof. Well, actually, we just did this. We proved, remember? We assumed there's non-leading columns. We got solutions in terms of lambdas, and those lambdas could be anything. So therefore, infinite solutions, we just proved this for the unique variable case, which is surprising. Now for this case, we'll look at this carefully. So suppose you have infinite solutions to this. Infinite solutions means, well, not a unique solution, right? And now we can actually use the unique solution theorem. Because there's not a unique solution, it means one of these conditions is not met. So either we have a contradictory row or we have a non-leading column. We can't have a contradictory row, otherwise there'll be zero solutions. But we have infinite, so that won't work. Instead, by elimination, we have to have a non-leading column. So therefore, we've proven it. We've proven this other direction. We've proven both directions. And so there's infinite solutions if and only if there's no contradictory row and there's a non-leading column in the row echelon form. Thanks for watching. If you have any more questions, leave them in the comments. Hopefully more linear algebra videos coming soon. See you next time.